Throughout this entire school year, we've had to go through physics. Some of us found it easy, but most found it hard. But now, we're at the end. This video project marks the end of it all. In this project, we'll show what we have all learned as a class. And today, we'll show you what my group has learned and decided to talk about during this entire project. I hope you enjoy.
There are 3 ways to change velocity.
The first way, hit the gas pedal.
The next way to change the velocity of a car is to hit the brakes.
The last way to change a car's velocity is to turn.
Next, we're talking about the Doppler effect.
The Doppler effect is an increase or decrease of frequency.
When Addison is driving her car, as we saw earlier, as she is moving towards us, the sound waves coming off of the car, she's following them, so they stay close together like this. And since a higher frequency creates a higher pitched sound, her car horn sounds higher. And then as she's moving away from it, the sound waves are moving away from the car, and the car is also moving away from the sound waves, so they move apart like this. And since lower frequency makes a lower pitched sound, her car horn appears to move lower. Here's our visual representation. Okay, so I am the car, and Bree is the sound waves in front of the car. So as you can see, as we walked, we stayed close together because as she was moving away from the car was following her. So that's why there is a higher frequency in the sound waves in front of the car. Now we're going to do a visual representation of the sound waves behind the car. So I'm the car, and Bree's the sound waves behind the car. So as you can see, as the sound waves moved away from the car was going forward, so they got even farther apart than if the car was standing still. And that is why there's a lower frequency on sound waves behind the car. Next, we're going to talk about mass versus weight. Weight is relevant, so it's different in different places, like on the moon, and mass is the same no matter where you are. Yeah.
For example, the bag is heavier than these keys, but they're going to hit the ground at the same time.
This here is Wilbur. He, on Earth, is 5.1 kilograms and weighs 50 newtons. This is because weight is the amount of gravity that pulls down on an object.
On the moon, Wilbur's mass is still 5.1 kilograms, but his weight completely changed. His weight is now 8.5 newtons. This is because the moon's gravity is much weaker than the Earth's gravity.
Since we're talking about mass, we should talk about Galileo's experiments on the Leaning Tower of Pisa. Galileo discovered that mass has no effect on how fast objects move in free fall as long as there is no air resistance.
Let us talk about Newton's first law. Now, Newton's first law can be summarized with the following sentences. An object at rest stays at rest, and an object in motion stays in motion. Now, if we go down here to my diagram. So here we have a block. It is at rest. So it will continuously stay at rest unless another force is exerted on it. Now here, we have a ball. Now assuming that there is no resistance whatsoever, if we were to push this ball in this direction, it would keep going on and on forever. Say we pushed it at 50, kilometers. Yeah, sure, kilometers. Now it will continuously move at that same speed unless something else, forces it to stop doing that. Say, for example, this block. Now, this block is a square. Well, yes, it's square. It's 2D. So, the block would stop the ball from moving. Let's talk about Newton's second law. Newton's second law states that acceleration depends on the mass and net force put upon an object. Now, acceleration is similar to net force. This is important because if we look here, 50 newtons of force will not push a ball of the same mass as much as 100 newtons of forces. This proves that, depending on how much net force is exerted upon an object of similar mass, affects its acceleration rate.
For every action, there is an equal and opposite reaction.
Okay. An example of this is when I hit Bree,
Ow!
her arm hits me back with the same exact amount of force as my hand hit her. Next, we're going to talk about centrifugal force. One of the easiest ways to see centrifugal force is to fill up a sink with water and then pull the plug. To better explain this, here is a visual representation. Since we know that every force has an equal and opposite reaction force, we can actually prove that centrifugal force doesn't exist. This is because it is actually just the opposite in reaction force to centripetal force, which is a real force. Have you ever wondered why when a balloon pops and you're holding it, it stings your hand? This is because the balloon is filled with atoms that have potential energy. And then when the balloon is popped, they're set into motion really fast, and the change from potential energy to kinetic energy can sting your hand. Right now, at the top of the slide, Bree has potential energy. When she slides down, she has
Kinetic energy!
the chains on Bree's tire swing, and she has potential energy. But when I let go, she has kinetic energy.
I need to try and explain potential and kinetic energy a little bit more. So here we have a ball on a string. Now these are two separate points for the ball. We'll call this one point 1, and we'll call this one point 2. Has a bad 2, but so these two are when potential energy is at its highest. Now, potential energy comes from the placement of the object. Now, it's called potential energy because, well, it's energy that can potentially occur. Like, for example, if the ball were to go straight down, because it's going to swing back and forth. Don't mind my camera. Give it a minute. So here is the point with the most kinetic energy. So it swings here with all this potential energy, gathers up and swings down. Now when it's here, it has the most kinetic energy because it is essentially the point where the most motion in the object is, and where, well, most energy is exerted outside the object. It will then swing back up, and since pretend that these are on even lengths, 0.1, 0.2, so that means that since they're both on even points, that they will both have the same potential energy, and when they swing down, it'll go back to having kinetic energy. Here we have water. Today I'll be showing you all the different forms that water can take and the different processes it goes through that go into these states. Here we have a cup of water. Now water in of itself is a liquid. As a liquid, water can go through different processes to become a solid or a gas. Now, first up, we'll be talking about freezing. Due to the lack of ice that I have in my freezer, this is going in the freezer. Here, we have boiling water. Now, water boiling is actually a cooling process. This is due to the fact that when water is boiling, the heat is actually escaping through the top, which we can see through this position. It's hard to tell, but there's steam coming out. This is the heat turning into a gas. Therefore, the water is changing into a gas state. Now, while we're here, let's turn the heat on to low. Just drop an egg in there. Actually, it's probably best that I don't do that with my bare hands, so let me just grab this. And we're just gonna pop that baby in there. And now, I'm gonna enjoy myself a boiled egg. Turn the heat back up, and we'll check back on that later. Now here, we have, well, the frozen water. Let me get it out. We have ice. Now, ice, well, we all know what ice is. I don't need to explain it. So, what we do know is that ice is a solid form of water. Now, this happens because while cooling, the energy lowers and the molecules of the water slowly clump back together, forming into a solid. Now, this I did not let freeze long enough, but it's fine. Now, like magic, it turned back into a liquid. Now, this happened because when put at room temperature, more energy in the molecules allowed more movement, which caused it to form back into a liquid. While I was filming the freezing portion, the egg popped. Mainly because I wasn't keeping track of the heat, so let's just take a look at the inside. Oh, yeah, that is not cooked, guys. Let's try that again. That egg not working out was actually something good. Now, this is because I can now explain why salt makes water boil faster. Now, if we pour some salt into there, that should be good. Yeah, maybe a little bit more. Okay. So, essentially what salt does is it traps the water molecules in place, making it harder for them to move freely, therefore boiling the water faster. So let's put a top on this and let that come to a boil. We have another cup. A happy birthday cup. But it's not about what's written on the cup. It's about what's on the cup. If we look here, oh my, this is a very dirty cup, but if we look right about the top, we can see water droplets. This is known as condensation. Now, condensation occurs when the air cools and the humid air, which trapped water vapor, has released the water vapor inside. And it tends to do this on the cup. Now, I'm going to wash this cup. See here, the water is back to a boil. Now, this is good because now we can properly make a boiled egg. So if, hold on, my spatula's on the other side of the room. Okay, so we're just going to take this and just plop that in there. Mix this up a bit, 'cause, you know, the salt's on the walls. Now this time, I'm going to use my brain, turn the heat off, and move this off the heater. My stove is just a bit messy, guys. It's fine. Now, okay, we're putting it back on the burner, just for a bit longer. Okay, just gonna leave this here, just for a bit. This is turning into a cooking show. Here's the egg now. So, now we're just gonna scoop it in. Oh boy. You know what? It'll be fine. We're just gonna transport this into this bowl. As I said before, I lack ice, so plain water is gonna do. Oh, that is still messy from earlier. Again, with my the physics video now turned to a cooking show, we have this boiled egg, and just like magic, it's peeled. Now, let's just make a small cut down the middle. Now that is definitely a boiled egg. Now it's time for the taste test. We're just gonna do that. Bon appetit. Oh. I've learned a valuable lesson today. I can confirm that I put way too much salt into that pan, and now it is a really salty egg, but I'm sure the yolk will taste different. But I'm sure you guys do not want the rest of this video me be eating the rest of this boiled egg, so I'm just gonna end it here. I hope you did enjoy that beautiful physics video and my entire cooking process. Trust me, I definitely know how to cook boiled eggs. Master Chef here, Rival Gordon Ramsay, signing out.